So we got this situation. We talk about escape speed. Let's do some calculations. An escape speed for a one solar mass object. Now, a one solar mass object is an object that has the same mass as our sun. So it's funny. We don't like to think of ourselves as egocentric or whatever, but we base a lot of our measurements on stuff that's just like lying around, right? So the sun is a solar mass. We use it as a unit of measure sometimes. Now, the radius of the sun is 6.95 times 10 to the power of 8 meters. It says that this object is a 100th of that. So if you know how to deal with scientific notation, that means that the radius of our object, 100th of that, is going to be 6.95 times 10 to the power of 6 meters. See what we did there with the exponents on the 10 to the power of? That's 100th of, right? Say, okay, well, if I was going to escape from this, that is with a projectile, 2gm over r, using that formula that we just derived, we can plug in our values 2 times, well, the universal gravitational constant, 6.7 times 10 to the power of negative 11 Newton meters squared per kilogram squared, times the one solar mass object, 1.99 times 10 to the 30. I need some people that are quick on the draw with the calculator to make sure this is going to work out for us. And then the mass is going to be 6.95 times 10 to the power of 6 meters. Sorry, the radius is 6.95 times 10 to the power of 6 meters. And then we square root the whole shebang. And my rough notes say that it should start with a 6, but maybe you guys tell me if you got something that starts with a 6. And like any of these ones with lots of scientific notation, sometimes it's the data entry that gets you. So make sure you can put this into your calculator. Anybody get one that starts with a 6? Everybody's too shy. Okay, we'll do it by confirmation. Yeah, what'd you get?
6180335.
Nice. That's exactly what I got. I love it. And it's meters per second. And so we say, okay, well, converting this over to scientific notation, we say that would be 6.18 times 10 to the power of, is it 6 meters per second? And we say, okay, well, that's not a slow object. It's a pretty fast object that got shot off of this like sun-massed thing. Is it reasonable? Well, I mean, being that the universal speed limit is 3 times 10 to the power of 8 meters per second, it doesn't break any laws that I know of. So yeah, this could be a thing. Let's play with another object. We get a 25 solar mass object. So you could actually do the math on this one, or you can just put into your calculations 25 times 1.99 times 10 to the power of 30 kilograms. That's a 25 solar mass object. And it says that it's going to have a radius that's 1/10,000th of the sun's radius, 10 to the power of negative 4. So we can do it this way. We can say the radius of this object is going to be 6.95 times 10 to the power of 8 meters times 10 to the power of negative 4. So 1/10,000th of that. And we calculate the escape speed. So we say, okay, the escape and I'm not going to rewrite the formula. I'm just going to sub in this time. 2 times 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass this time is 25 times 1.99 times 10 to the power of 30 kilograms, all divided by 6.95 times 10 to the 8 meters times 10 to the power of negative 4, all square rooted. And again, a big challenge here is data entry. I'll give you the helpful hint that it starts with a 3. I'll give you the other helpful hint that it's not a small number. What do people get? Starts with a 3 and not a small number. Did you get it? No? Oh, yeah, like a look of satisfaction on your face. So I thought maybe you had it. All right. Well, this is what I got. Okay, you guys tell me if you match up with me. People that did it, does that look right to you? Boy, that's a big number. I'm going to throw in some commas just so that we can see where all the zeros or all the thousands are on this one. If I was going to turn this into scientific notation as I turn it to three significant figures, notice that I get approximately 3.09 times 10 to the power of 8 meters per second. Now, you guys can see as well as I can what the subtitle for the next section is. And you guys can see as well as I can that the speed limit for the universe is this. What's the object? This is a black hole, right? There is no particle ever that's going to escape from this object, whatever this object is, because the calculated escape speed is greater than the maximum speed for the universe. This is something that nothing can get away from. Everybody on board with this idea? Right? So if you're not on board with this idea, that's okay. You don't have to be. But that's the math. Yeah.
On the last page, you said that the mass that doesn't get canceled out, so
Yeah.
is like the mass of the Earth, but for this one, the mass of the object gets canceled out. Like, how come these ones, the mass of the object like, stays as
You're saying in the previous one, the mass of the object got canceled. Let's take a look at this. The previous one we were looking at, it was the mass of the escaping object that got canceled out and the mass of the body being escaped that got kept. And with this one also, it's the same question. Basically, it's an extension. It's the mass of the body that's being escaped that's being kept. Okay? And the mass of the object that's escaping cancels out. So what we're saying here is regardless of the mass of the projectile trying to escape, it won't get away. So this could be like an alpha particle or it could be a pickup truck. It's never getting away. Okay? That's nice. Yeah.
So the extra refinement is like the speed a mass needs to escape the body.
Yeah, this speed here, this escape speed, I mean, it's built into the name. The escape speed is the speed that an object needs to escape from a gravity well. Okay, and I've drawn gravity wells, but there's this little infographic here on the right-hand side, and just as a cartoon, I don't even remember where I got this cartoon from. I'm not going to lie, it probably came from my Facebook activity feed because the algorithm knows what I like. But every time I see something I like this, I steal it and I throw it into my notes. And I really should credit things, but I'm not making any money off of this anyway, so whatever. But this idea of space-time being stretchy, and this idea that when we talk about, like a moon that creates a gravity well, or a planet versus a star that creates a gravity well, versus a black hole, and my math hat comes on and I'm thinking like these black holes, my goodness, the gravity wells almost look like an asymptote. You see what I mean by that? And if you have a gravity well that looks like an asymptote, this is where, and you might have heard this in sci-fi talkings, or you might have heard it if you're really into reading science articles. This idea of an asymptote around a gravity well that causes a black hole, this is what people call a singularity. And there's a whole family of math around dealing with singularities. Now, there's people who use the word singularity for what's going to happen with AI perhaps one day. But a singularity when it comes to a gravity well is something that has walls so steep that the mass is packed down so tight that it's like it happens at a point in space and you can't get away from it. That would be a singularity in a gravity well, okay? So I'm just throwing that out there because it was a cute little cartoon that probably came across my social media, but I think it explains this idea really nicely in a cute little cartoon kind of way, What do Calvin and Hobbes have to say today? Hey, do you know, and this will date the video a little bit, But Kelvin and Hobbes turned 40 years old this week. That's crazy. Time flies. Also, I got this message yesterday, happy birthday. And I was like, it's not even my birthday. And it was a 14-year-old birthday card for my YouTube channel. I was like, wow, time does fly. All right. So Kelvin and Hobbes are here talking about something called a Schwarzschild radius. Um, some German astronomer named Karl Schwarzschild. And I love Schwarzschild because I think like Schwarz, isn't that black in some language? I thought it was. Anyway, and a child, like the dark child. And so we're talking about black holes here. And so um, this Schwarzschild radius, which we're about to calculate, this is the radius of a black hole. He calculated it first in 1916. And sometimes when we talk about this type of physics, people call it modern physics. Modern physics just happened relatively recently. It's not that it's like modern and cutting edge that happened last week, although the thing that happened last week is also modern physics. But oftentimes this kind of thing gets thrown into the umbrella of modern physics. I used to say because it happened within the last 100 years, but that's not even within the last 100 years anymore, right? So this is the knowledge of our grandparents. And I had a girl in here one day. She said, my grandpa studied this when he was in high school. This isn't really modern anymore. And her grandfather were laughing about that fact, right? He had done. I can't remember where they were from. I think it was Afghanistan he was from, but he had learned this when he was a kid. I just thought that was so cool. All right. So this is a conversation that some of you could have with your grandparents, depending on their academic background, right? And I think that's great. Coffee table conversations, dinner table conversations. So this escape speed, the escape, being equal to 2 times gm over r square rooted. Now, if I do a little bit of work with this, what Schwarzschild said was we'd like to figure out how big a black hole is. Let's get the radius of a black hole. So we square both sides. We want to get the r all by itself. And then we say, well, the escape speed for a black hole, wouldn't the escape speed have to be related to how fast light can travel? Because we'd say, okay, the radius of the black hole is defined as the radius from which only light can escape, or not even light can escape. Yes.
Shouldn't that the escape be squared?
Well, you're right. It should be squared. Thank you for catching that. You're right. Yep. So if we want to talk about the radius from which not even light could escape, we're going to sub in, instead of v escape, we're going to say let v escape equal c, where c is the stand-in for the speed of light. So if I sub that in, I say 2 times g m over c squared. This little cartoon that Kelvin and Hobbes are talking about here, of course, that's not the original text. I infringed on something or other, I'm sure, and I replaced it with a conversation about Schwarzschild radiuses. But still, it's a good thing to think about at bedtime. Schwarzschild radius this is the radius from which, or radius within which, I should say, not even light can escape. And some of you have probably even heard the term, well, the edge of this is the, how many people have heard the word event horizon? You heard the word event horizon? Sometimes people throw around event horizon in erroneous ways, like, oh, once we get past this event horizon, it's all downhill from here. This is the last thing that's going to happen before the big fallout in the economy or something like that, right? And that's like a nice illustration. It's like your economy is about to go into a black hole or something like that. But the event horizon literally would be the orbital radius for light. around that black hole. Anything that happens at that horizon would the light from that event would be locked in orbit. That's weird. Like anything that happens as an event would be stuck in orbit around that horizon. That's a wacky idea. I mean, if you could stick in a camera right into the event horizon, you couldn't because the gravity well would tear it apart. But if you could, and you could take pictures of everything that black hole had ever seen, what an amazing thing, right? That would be so cool. You can't. Don't worry about it. All right. So the edge of this is the event. I ran out of space. Event horizon. And I have here an artist's rendition of a black hole, but then just below, I have a satellite. Sorry, not a satellite. An orbiting telescope picture of a black hole, and the glowing ring around it is that event horizon. Okay. All right, so I want to do an event horizon calculation. We know that the escape speed for this event horizon would have to be the speed of light. We say that the mass of this particular black hole is 10 times the mass of the sun, so 10 solar masses. So C is equal to 3 times 10 to the power of 8 meters per second. The mass of the object is 10 solar masses. We sub in our values. Oh, sorry, I didn't rewrite the formula. The formula that we're using is this one right up here. I'm a bad person. I'm sorry about that. And you don't want to forget to square the speed of light. Ho ho, we never want to forget to square the speed of light. All right. And you can check to make sure all of this works out in terms of the units, but yes, the units really do work out. I'm going to put it out there that I get 29,496.2 repeated meters. In other words, the radius of this object, if it's a black hole, is 2.95 times 10 to the power of 4 meters. If I want to put that in the language of kilometers, 29 and a half kilometers. All jam-packed into one little space. All this mass, 10 times the mass of our sun into 29 kilometers. That's a lot. That's a high-density object. I mean, it's hard to know how high density is from your everyday math because you don't really have a good concept of how big the sun is. 29 kilometers, though, that's less distance than from here to the next town over. And 10 suns packed into that space, that's a lot, right? So even if we have a hard time with the number sense on that one, that's a lot. Okay, we have a really dense object here. Won't even let light get away.